All right, I just recorded a video on exhaust back pressure for a car, and my mic wasn't on, and it was 40 minutes long, and I'm mad. But now I am redoing it. Hopefully it's more organized than this one, because this one wasn't very organized. So the whole goal is to calculate how much power you lose through back pressure in your car's exhaust. I think it's pretty neat because I like car stuff, and we're gonna freaking cover it. So, cool. So you've got your car's engine, and it's got its exhaust, which we're just gonna assume is a pipe, and it shoots out the exhaust gas in the back. So your car, the engine, it makes power, and power is, what's a good symbol? Well, okay, I'm gonna call it W. It makes power. And this power is the power of the engine. Well, I'm gonna call it power net. This is how much power goes to the wheels of your car, and you want that number to be as big as possible. Wheels is engine minus a bunch of stuff. One of them, and the one we're going to talk about here, is back pressure exhaust. So if you want to maximize the power to the wheels, you want to minimize the exhaust back pressure. Cool. So how do we calculate exhaust back pressure? Well, how do we calculate power? There are a lot of different formulas. The one that I'm going to use is force times distance, which also equals pressure times area times distance. Cool. How is that helpful? Well, let's talk about the area first. So let's assume your car's exhaust is all the same diameter everywhere, which it isn't, but it's the same idea whether it is or it isn't, and it's easier to convey the idea if it is the same diameter. So let's assume it's the same diameter. So the area would be pi r squared. That's it. What is the x? So inside of your engine, you've got a bunch of pistons. I'm gonna just draw one piston, but you have a bunch of them. And you got your piston there, and then it goes up to there, and then it goes down to there. So the x is how far you move this chunk of air in your exhaust. It's how far you move this chunk of air. So you would move that chunk of air equal to the amount of volume that you push out of your piston. And the amount of volume that you push out of your piston is, I'm gonna call this an area, and then this will be H. So it's area times height. So that's the volume of air that you push out of your piston when you push it into the exhaust. And that volume also has to equal A of the exhaust times X. And X is this distance, X. So far, I think it's pretty straightforward. So X is, I don't even know what to write for it, but you get the idea of what it is. Cool. And then the pressure, this is the most complicated one. But it's not really that complicated. So pressure, what pressure do you care about? You care about the pressure right here, right at the inlet of the exhaust. And I'm going to call that state 1, and you'll see why in a second. Actually, how do I do that? How do I do this nicely? Here we go. So I'm going to call this state 1, and state 1 has a pressure and it has a velocity. We'll leave it at that. And then at the exhaust, you have state 2. That has a pressure and that has a velocity as well. So how do you calculate the pressure here at state 1? So the way you do that is with the Bernoulli equation. And you learn this in Mechie undergrad in your fluid mechanics class. And it's very powerful. If you learn anything from that class, learn the Bernoulli. People talk a lot about Navier-Stokes and, oh my gosh, it's so complicated and it's so useful. It's only useful if you're doing aerodynamic stuff. Bernoulli is useful like everywhere. So learn Bernoulli. Cool. So what is the Bernoulli equation? It is P1 over, looking at my notes. This is over density gravity, not 2 times gravity. Okay. Looks pretty complicated. What exactly is it telling you? So let's assume you learn this in freaking high school physics. So you have a box with a mass, m, and you drop it. And it hits the ground. And you're asked, how fast is it going when it hits the ground? So the way you do that is you say, let's call this state 1. Let's call this state 2. So you say mgh plus 1/2 mv squared at state 1 equals mgh plus 1/2 mv squared at state 2. And this is literally just an energy balance. You're saying that the total amount of energy, this whole thing is energy. Energy at state 1 equals energy at state 2. And at state 1, all of your energy is height. It's not moving. It has a velocity of 0. And at state 2, all of your energy is in velocity. It has a height of 0 because it hit the ground. So you end up with mgh equals 1/2 mv squared. You learn that in high school physics. I'm assuming this makes perfect sense to you. So this is literally a fluid's energy balance equation. So you have your velocity, you have your height, you have your velocity, you have your height. There are a couple extra terms though. You have a pressure term because another way to store energy is with pressure. You have a pump term because pumps can add energy. You have a turbine term because if you push fluid through a turbine or like a fan, it'll take some of the energy away because now you're physically spinning a fan. You also have a loss term, and this loss term is like the friction loss if you're going through a pipe. It's also like if your pipe has a bunch of bends, then the loss term will be super high. We'll explain it in a second. So, cool. What do we have in this equation? Assuming state 1 is at the inlet of the exhaust and state 2 is at the outlet of the exhaust. So, we're going to have a pressure. We're going to have a velocity. Let's assume that the height is negligible, like the change in height is negligible between the exhaust inlet and the exhaust outlet, because it probably is. There's no pump in between the inlet and the outlet. There could be a turbine. There could be a freaking turbocharger in here. That would be classified as a turbine. And if there is, it complicates your Bernoulli equation and all that stuff. But let's assume you got freaking Honda Civic. It's not turbocharged. Let's assume you just go to the store, buy a Honda Civic. It's naturally aspirated 4-cylinder and it makes 50 horsepower and you're chilling and you're happy with that. Let's say that's this car. So there's no turbocharger in the car, or you get a freaking Mustang and there's no turbocharger in that unless you get the Mustang with a turbocharger. And who buys a Mustang for a turbocharger? All right, anyways, let's assume this term is 0. So you're left with, what are you left with? I'm going to rewrite it to group some terms. All right, cool. So all I did was move this stuff over to the left. And that was it. So this is saying if your loss in the pipe increases, so like you have more bends in the pipe or the friction in the pipe is higher, I'll write that equation down in a second. That means the difference in inlet and outlet velocity, or the change in inlet and outlet pressure, like the delta between these two, either one of those has to go up or both of those have to go up. And for the case of argument, I'm going to say this term, the V1 minus V2, that's always going to be constant. And that technically isn't true, but it's mostly true. And the reason why is because if we say, well, okay, let's assume that the exhaust air is incompressible and it's not changing density. That is it's an okay assumption. It's not a great assumption because it's super hot here. T1 is super hot and T2 is colder. And that's because of heat transfer. And as the exhaust gas cools, it becomes more dense, which means it would flow slower. But let's assume it's constant temperature, constant everything, and we're just chilling. So we have how much volume is being moved on this right hand. Well, what's the mass flow rate on the right hand side? So mass flow rate equals density, velocity, area. Let's assume area stays this. Well, all right, we'll get to that. So that's mass flow rate equation. Here we also have a m dot equals density, velocity, area. Cool. What do we do? So let's assume the areas are the same, or even if we don't assume they're the same, they're not changing with time, because your exhaust isn't getting bigger and smaller unless there's thermal heating, which there technically is, but that's another story. Let's assume it's not changing. So let's assume the areas are the same, so they cancel out. And the reason why I'm doing this is because m dot in has to equal m dot out, because the mass in has to equal the mass out. So those are the same. Let's assume the densities are the same. Cool. So all you're left with are the velocities. And this means, well, in this case, V1 equals V2. If your exhaust diameter just gets bigger over time, like your exhaust just grows, then it would be like V1 equals V2 times like A2 over A1, something like that. But let's assume it's the same diameter, inlet and outlet velocity are the same and all that stuff. So V1 has to equal V2. Or if not, even if it's times like A2 over A1, it always has to equal A2 over A1 times V2. Like it always has to equal that, no matter what's going on in the middle, because mass has to be conserved. So let's assume this term is also 0. The difference in them, it's either 0 or a constant. And if either way, it doesn't matter because we're just looking at trends with time, what changes with time. So cool. That's my argument for how to cross that out. So we're left with density times gravity equals h loss, which equals sum of v squared over 2g Cool. So what is this term? This is saying that the loss through the pipe would increase, as in it would be harder to push stuff through a pipe if it has a bunch of turns in it, versus a straight pipe. A straight pipe won't have any bends in it, so it'll be super easy to pump stuff through it. tube or a pipe with a lot of bends in it is harder. So you can literally Google these KLs or look them up in like a textbook or something. They literally have tables. Like they'll say a freaking 90-degree turn is like a KL of 0.5 or whatever. It's just some number. It's like a fixed number. That's it. So for this example, there's 1, 2, 3, 4. So KL would be 4 times 0.5. That would be KL. And let's say you have, I don't know, let's say you also have a converging nozzle or something, and let's say that has a KL of 0.2, then you add a 0.2, and that would be your KL. So literally the more bends, the more stuff you have that stops it from being a straight pipe, more orifices, all that stuff, means your KL term increases, which means your H loss increases, which means the difference between these two terms has to increase. Between pressure 1 and pressure 2 has to increase. Likewise, and I'll get to the significance of the difference between pressure 1 and pressure 2 in a second. So that's KL. What is this right-hand term? So D is diameter of the pipe. L is the length of the pipe. What is F? F is the friction in the pipe. So let's assume they didn't machine your like exhaust pipe super well. So it's super rough. Got a super rough surface. Now I'm over exaggerating. No exhaust pipe is a rough surface like that. But let's just say it's super rough and it's, yeah, a rougher pipe is harder to pump stuff through. So this would have a rough pipe, would have a higher friction coefficient, which would increase head loss, which would increase this delta pressure. Okay. So if we solve for P1, we get P2 plus density gravity times head loss. Okay. So what is P2? It is a number and it's easy to calculate. It is literally atmospheric pressure. So P2 equals P atmospheric. If you want to get lower P2, you'll go to a higher altitude. So you go to like Colorado or something. But if you do that, you're also going to be in less dense air, which means your engine's not going to pull in as much air for the same volume, which means it's going to produce less horsepower, unless your car is turbocharged, in which case that kind of negates the elevation effect. Anyways, cool. All right, let's walk through something from start to finish. So let's say you initially had a straight pipe like this one, and now you have this super bendy pipe. So that's going to increase KL, which will increase head loss. So this term will go up, which will increase P1, which will increase P1 over here, which will increase the W exhaust back pressure. And if your exhaust back pressure, if more of your car's energy is spent pushing exhaust gas out of the exhaust, less of it is spent on spinning the wheels. So there you go. You want to spend the least amount of energy pushing exhaust out of the exhaust. Okay. So if there's a lot of bends, it'll increase KL. If it's super rough, it'll increase the friction factor, which will increase head loss, which will increase P1, which will increase the exhaust back pressure. Exact same idea. So both a lot of bends and also super rough pipe, not good. What's another example? Let's say you have a super big diameter pipe. Massive diameter pipe. And some cars have stuff like this. So what would that do? Well, that would decrease the magnitude of this whole term because the diameter would increase, and it's 1 over diameter, and which means this whole term will decrease. It'll also decrease the velocity, so that's another decrease arrow. And the reason why is because your engine's still shooting out the same amount of volume of air. Again, I'm kind of assuming volume and mass are interchangeable. Technically they're not, but for the purpose of this, I'm assuming that. And so it's still putting the same volumetric flow, right? But now, so it's area times volume, but now with a bigger diameter, area increases, and this stays the same, so velocity decreases. So for this term, diameter is increasing, which means this whole term decreases, and velocity is increasing, which means velocity is decreasing, which means this whole term decreases. So it decreases double. And this term, even though the amount of bends in the pipe didn't change, this whole term decreases as well because the velocity decreased, which means head loss decreases, which means that P1, probably don't have to draw the arrows, you probably understand where this is going. P1 decreases, which means exhaust back pressure decreases. Cool. And that means more of your engine's power goes to the wheels, which is what you want. So again, in summary, more bends is bad, more friction is bad, bigger diameter pipe is good. Okay, now, one way to decrease exhaust back pressure is to decrease P1, and to decrease P1, you either decrease P2 or you decrease the loss, and the loss is the pipe diameter, it's the velocity, it's the losses, it's a friction factor, it's all that stuff. Now, is there a way to decrease P2? And the answer is yes, there is. And it's freaking neat. So some cars put on an exhaust that points downwards, like towards the ground. Like it goes to the lowest point of the car and points downwards. And why do they do that? It's freaking sick. So, all right. So you've probably experienced this before. So you're in your car, you got your window open, your car is going that way. This is your window, by the way. So your window's open, and then you close your window, and your ears pop. And your ears pop when there's a change in pressure. And why did the pressure change when your window is open versus when your window is closed? And the reason is because of the Bernoulli equation also. So let's say point 1 is somewhere way off in the distance, and it has P atmosphere and a velocity equals 0. Yeah, because it's not moving, it's just air off in the distance. And then your point 2 is air that's right next to your car. Let's actually say it's right on your window, like it's flowing by your window. And this would have a P of, we'll get to it, but it'll have a velocity of something that's greater than 0. So it's greater than 0. So, all right, let's write out the kind of the relevant terms of the Bernoulli equation. Some stuff plus v1 squared over some stuff equals p2 over some stuff plus v2 squared over some stuff. Cool. So conservation of energy. Up here off in the distance, you had 0 velocity, and now, from the point of view of your car, the air has a velocity. Not exactly, well, I'm not exactly sure if the point of view of your car is the right argument. It could be that no slip condition on your car is dragging the air forward. Either way, the velocity is greater than 0. So PATM, and this pressure would have to be, so you'd have a P, well, how do I draw this? 2 is less than PATM, and velocity goes up. So, I don't know if I drew it out that nicely. There's probably a better way to do it. But the idea is before all of your energy was in pressure, and now all of your energy is split between pressure and velocity. So by default, that means that the pressure, P2, has to be lower than P1. Hopefully that explains it decently well. So, if the exhaust is just sticking out straight back, there's a lot of aerodynamic stuff and fluid modeling that goes into it. But the idea is you could assume it's at atmospheric pressure, even though stuff around it's kind of moving, but it's kind of moving and curling back on itself and that sort of stuff. So it's, yeah, that's a whole nother discussion. But if you have the back pressure, or if you have the exhaust pointed like down, air is flowing over it at a velocity, which means that the pressure, P2, is less than PATM. So, cool. That's pretty neat. That is actually pretty neat. So in summary so far, well, okay, so there are cars that do this besides just special race cars with aftermarket exhausts. Like the Viper does it. It has exhaust pointed out the side for the exact same reason. McLarens, I think, some McLarens, and I think there's a Porsche that had the exhaust like kind of on the roof pointed upwards, and it's the exact same idea. Like it had the exhaust like here or something. It's the exact same idea to get the airflow to go over it. And the Viper, it's got the exhaust like on the sides to get the air to flow over it. So there's cars out there, like stock cars, that take advantage of this principle. And again, if P2 decreases, P1 decreases, which decreases exhaust back pressure, which means more of your power goes to the wheels, which is great. That's exactly what you want. Pretty freaking sick. All right, what else did I expect? Oh, yeah, okay. So far we've talked about bigger diameter is good. Lower friction in the pipe is good. Fewer bends and orifices and that sort of stuff is good. If the exhaust is angled such that air is flowing over it perpendicularly, that is really good. There is one more thing. So it has to do with RPM. If your engine is spinning at low RPM, where did I draw it? Yeah, I drew it right here. Okay, so if your engine is spinning at low RPM, so if H is low, H dot is low, that means the volume dot is also low, which means yeah, let's go with, there's two ways to do it, which means this is low. Nope. Which means this is low. Area is the same because your exhaust doesn't change area, which means the X is low, which means that's low. This X is low. So the exhaust back pressure is low at low RPM. You can also prove it. So this X is, you could think of it as X dot. It's basically the velocity. It literally is the velocity because the rate of change in X is dx dt, and which is X, or meters over second, which is literally velocity. But another way to do it is if you're at low RPM, the exhaust velocity is low, which means the head loss is low, which means this is low, which means the pressure is low, which means the pressure is low. There you go. Both of those ways work, and I think they'll stack on each other. I don't think it's wrong to double count them, but I might be wrong about that. So at low RPM, you're going to have low back pressure. So let's make a plot of this. RPM versus, call it P1, and we could also call it, I won't call it P1, I'll just call it the most broad one, which is W exhaust back pressure, this variable. So we said at low RPM, you're going to have a low exhaust back pressure, and at a high RPM, you're going to have a high exhaust back pressure because, again, if this H, the rate of change, oh, that was A. If the rate of change of the height, so if the piston's going up and down really fast, it's pumping, it's literally pumping, it's pushing out a lot of volume of air really, really quickly, which means the velocity increases. Both of those increase, which means the head loss would increase because this velocity increases, and it increases at like squared, which is even worse. Which means pressure increases, which means this pressure increases, which means this value increases. So I'm trying to do my best to show, like, from start to finish how to tell whether a modification will help or hurt. But anyways, so it'll look like that. It might be a parabola. It might look like that. I don't know. I could think about it and probably tell you generally, but I don't really care. The idea is as RPM increases, exhaust back pressure increases because the exhaust velocity will increase. And the exhaust velocity increases because the engine's moving, like pistons are moving faster and they're pumping out air at a faster rate. Cool. So let's say you get an exhaust with a bigger diameter. How would that change this curve? So you get the bigger diameter, kind of talked about this. The H loss term will go down, pressure will go down, exhaust back pressure will go down. So a bigger diameter will mean that you now have a different sloped line. Different slope line, it'll probably be lower. I mean, these both go to 0. But the idea is the slope of your line will be different. It has a massive D. Mini D. Yeah, okay. Cool. Yeah, so if you get an aftermarket exhaust with a bigger exhaust diameter, or any of these other modifications that reduce back pressure, it'll move this line down. And your engine is tuned for a specific back pressure, which is one of the reasons why, like, warranties, well, like, if you buy a car with a warranty, they don't really want you swapping out the exhaust because your car is literally programmed for a specific back pressure curve, And if you change the exhaust, you're changing that curve. And that could cause issues, maybe. I'm not 100% sure on it. But if it's going to cause issues, this is why it would cause issues, which is pretty neat. Anything else that I missed? I think that was it. So in summary, a bigger diameter exhaust is good. It means lower back pressure, which means lower exhaust pressure is lost, or lower energy from the engine is lost to the pumping fluid out of the exhaust. Less friction is good. Fewer bends in the exhaust is good. Lower RPM is good. And this really neat one, which is an exhaust that is perpendicular with the airflow, is really good because that decreases, I called it P1 and P2, but this, yeah, effectively it would decrease P2 if it's perpendicular with the airflow. Yeah, I think that's it. Let's go.